is I looked up overall just to give you an idea of like what it means for events to be dependent or independent. So overall, if you look at the probability of lung cancer in the United States, I know it's kind of like a morbid topic, but it'll make sense. It's about, 1.5%, maybe 2% in adult males. That's kind of what I found when I was doing some research here. So let's maybe call it like 1.5%. So as a decimal, that's 0.015. So a 1.5% chance you get lung cancer if you're just a random individual in the population. However, that changes significantly if you are a smoker. So if I do probability of LC, so I'm writing lung cancer, the probability of lung cancer given that you smoke is significantly higher, and that should make sense. Um, that number comes out. I got estimates 15 to 30 times more likely. So we'll say maybe it's around like 18%, something like that. Actually, 10 would be 15%. So let's call it 30%. Zero point 0.3. Maybe there's about a 30% chance that you get lung cancer given that you're a smoker, maybe like given that you smoke for a significant period of your life. So what this is evidence of is that these two things are not independent of each other. It's evidence that one thing affects the other. This probability going up to 30%, there's only a 1.5% chance you get lung cancer. But if you smoke, given that you smoke, that number goes up to something like 30%. So clearly these two things are linked. Clearly one is not independent of the other. Clearly you're more likely to get lung cancer if you smoke. And when we're thinking of probabilities in general, if we look at the overall probability of something, for example, like the overall probability of lung cancer, there's some like baseline rates, 1.5%. If you then look at that same probability given another condition, so given that you smoke, if that number changes significantly, that is evidence that condition was affecting the other thing you were looking at. So this is evidence that smoking affects the probability of lung cancer. Um, okay, so that's what we're going to look for here. And if these two numbers were the same, that would mean that smoking did not affect lung cancer, but clearly it does. All right, let's take a look at the question. So the question says there are 150 students in an 11th grade high school class. There are 45 students on the soccer team, 35 in basketball, 20 who play both. So the first couple questions it's giving me are given in the question. So it's saying this first one here, what is the probability of A? What is the probability a student plays soccer? So that's out of 150 total students in the class, 45 play soccer. So the probability, if I pick a random student, there is a 45 out of 150 chance that I pick a soccer player. So the answer there should be 45 over 150. All 150 are equally likely. 45 of them are on the soccer team. Same logic here for basketball. So it's going to be out of 150, but how many play basketball out of 150? They tell you in the question it's 35 out of 150. A and B, that's going to be soccer and basketball. Again, it's given in the question there are 20 who play on both teams. So if I randomly pick a person from this 11th grade class, there is a 20 out of 150 chance that they play both soccer and basketball. Now, this is asking A given B. So, what is the probability that they play soccer given that they play basketball? So, I'm going to use the conditional probability formula here. So, that's going to be probability of A given B. The conditional probability formula, if I want to find the probability of A given B, I think of it as a fraction where the denominator is the given condition, the second thing listed there. Denominator is probability of B. The numerator is going to be the probability of both. This is the formula for conditional probability you can look up. Um, let's see, reason why it works. So what we're doing here is probability of soccer given basketball. So I am thinking, given basketball, I'm thinking out of the basketball players. So out of the people who play basketball. How many people play basketball? That's 35. So the probability you play basketball is 35. Given that I play basketball, what's the probability I also play soccer? This number here, it's going to be the soccer players, but it also has to be the basketball players because it's given that they play basketball. The number here, A and B, that's soccer and basketball, that was given in the question is 20. I'm just going to write in the number 20, right? Because 20 people played both out of 35 who played basketball. So let me do this in a calculator here. Let me pause that. You get 0.57. 0.57. So what that means is given that someone is a basketball player, if I know somebody plays basketball, there's a 57% chance they also play soccer. So I'll put that in. I hope it takes that as an answer here, 0.57. But I could always just put in 20 over 35 here. But let's do 0.57 just to see if they take it. And then is the probability of A given B the same as A? So let's think about this. So A given B, that's soccer given basketball. Soccer given basketball. Is that the same as the probability of soccer? Well, the probability of soccer is 45 over 150. If you put this in your calculator, you get, let me do it real quick, 45 divided by 150. That is 0.3 equals 0.3. So if you take a random person from this school, there is a 30% chance they play soccer. 45 out of 150 comes out to zero point 0.3. If you pick a random person from the school, there's a 30% chance they play soccer. If you pick a random basketball player, that's what this is. If I pick a random basketball player, there's a 57% chance they play soccer. So if I know that someone is a basketball player, I know they're more likely to play soccer as well. That is telling me that these events are not independent. If you play basketball, you are more likely to play soccer. So I'm going to say they are dependent events. The probability of A given B does not equal the probability of A. That's the probability of soccer given basketball. That does not equal the probability of soccer. 30% compared to 57%. So no, those conditional probabilities are not equal, and that's telling me that the events are not independent events. In fact, they're dependent events, meaning that one affects the other. If you play basketball, you're more likely to play soccer. Let's see. It says not quite yet. Give it another try. I think it probably doesn't like the 0.57, so let's put it in as 20 over 35. Let's see if it likes that. Yeah, so can't use decimals there. Just stick to the fractions. I don't know why. I actually already submitted this as an issue to Khan Academy. I'm not sure why it doesn't do that. Okay, so next question here. It says that says to suppose that Adam rolls a fair six-sided die and a fair four-sided die simultaneously. So the picture down here is showing the sample space. So this is all the times where I roll a one first, two first, three first, four, five, six, and that's with a six-sided die. And then going across, this is rolling a one on the four-sided die, two on the four-sided die, a three, and a four. So in total, this grid is 6 by 4. So there are 24 total outcomes, and they're all equally likely. So the question is, let me go down. So this is what's happening. We're rolling a six-sided die and a four-sided die, and this is showing the sample space or all the possible outcomes. And what we're going to do is probability A. So what is the probability the six-sided die is an even number? That's just an overall simple probability question. So there's six sides on a die. What's the probability it's even? The even ones are 2, 4, and 6. So you can think of it as 3 out of 6. If you want to get, like exact with it, 3 of the sides of a die out of 6 are even, but you can also very simply say half of the time it's an even number, half of the time it's an odd number. 3 over 6 reduces to 1/2. So you can certainly just put in 1/2 for this. Half of the time you roll a six-sided die, you'll get an even number. And I think that's true with a four-sided die, half even, half odd, because it's 1, 2, 3, or 4. So for an odd number, that's 1 and 3. So that's a 1/2 chance. So if you roll a six-sided die, half the time it's even. If you roll a four-sided die, half the time it's odd. Fair enough. What is the probability of A and B? What's the probability the six-sided die is even and the four-sided die is odd? A couple of different ways you can do this. You can just count it in the sample space. What you might want to do is maybe just use let's count it in the sample space. Let's count in the sample space. So there's 24 outcomes here. How many of those 24 have an even number on the six-sided die and an odd number on the four-sided die? So the even number on the six-sided die, all the sixes are good, but I also need an odd number on the two-sided die. So it's going to be this one and this one. That's even on the 6, odd on the 4. I can also do that here. Even on the first die, odd on the second die. I'm saying the first die is the six-sided die. Here I have even on the first die, odd on the second. So these 6 that I have circled, those are the only ones that work. Those are the only ones where I have an even number on the six-sided die and an odd number on the four-sided die. So my answer there is going to be 6 out of the total possibilities, which is 24, and they're all equally likely. So I can just do 6 out of 24, or 1/4. Are these independent events? There are different ways to figure this out. What I might do is I might use conditional probability in the way that I talked about at the start of the video. So what I might say, let me change my color here. I might look at what is the probability of A? What's the probability of rolling an even number? on the 6. We already said that's 1/2. Is that affected by B? So what I'm going to do is I'm going to find the probability of A given B. And that's going to tell me, does the knowledge of B happening, does that affect the likelihood of A? What's the probability of A given B? So if I know B is happening, how likely is A? So the denominator here is going to be B. So it needs to be all the times where I roll an odd number on the four-sided die. That's B, and that's 0.5. We actually already have that probability of 0.5. And then A and B, that is both. So that's um, even on the first die, odd on the second die, and actually that's this here. So our numerator is going to be 6 over 24. And it looks a little weird, but this is how I'm thinking of it. 6 over 24 is the numerator, 0.5 is the denominator. If I want to simplify, 6 over 24, that's 1/4. So I can write that as 0.25. 1/4 is 0.25. If you put 6 over 24 in your calculator, you'll get 0.25, and it's over 0.5. And I already know this is 1/2 because 0.25 is half of 0.5. But if you put this in your calculator, 0.25 over 0.5, you should get 1/2. So what that's telling me, the chance of A was 1/2. That's my baseline. The chance of A given B. So did B affect A? Well, no, because if I find the probability of A given B, the probability of A does not change. So just because I know that I rolled an odd number on the four-sided die, that doesn't affect my probability of rolling even on the first. So in this case, those are independent events. Yes, they are independent events. Question is about a standard deck of cards. Sherry has one. The deck has 52 total cards. 4 suits, hearts, clubs, diamonds, spades. So it's describing the way cards work. So Sherry randomly selects a card. Let A be the event that the card is a king. So let's define the probability of A. Probability of A is the probability that you get a king. There are 52 cards. So it's going to be out of 52. How many are kings? If you know from the decks, if you're getting this as described, so there's a king in every suit and there's 4 suits. There are 4 kings. The chance that you get a king in a deck of cards is 4 out of 52. And oddly enough, that's true for any card, whether it's a king or a jack or a queen or a 3. So when it asks for B, is the probability that you get a 3, that should be the same thing, 4 out of 52. So for any individual card, there's a 4 out of 52 chance you get that card. There's 4 of them in the deck out of 52 possibilities. So now it's asking a bunch of questions and a lot of confusing language, I think. But really what it's getting down to is, are these things dependent or independent? So let's think about it for a second. If the probability of getting a king is 4 out of 52, does that change if I know that I get a 3? What's the probability of A given B? What's the probability of getting a king if I got a 3? Well, if the card I get is a 3, it's not a king. So the probability of getting a king, given that I get a 3, is actually 0. There is no chance of getting a king if your card is a 3 because it's a 3. So the overall probability, the baseline, the probability of getting a king is 4 out of 52. But if I do A given B, what's the probability of getting a king given that I got a 3? That is 0. If I think of it as, what's the probability you get a king given that it's a red card, there's 2 red kings out of 26 red cards. It comes out to the same probability. It comes out to the same 4 out of 52. So getting a king and pulling a red card, those are independent. It doesn't matter whether the card is red or black. You have the same chance of getting a king. But if you get a 3, you can't also get a king. So these things, they're not only are they dependent, they're another word for them would be disjoints or mutually exclusive. They cannot happen at the same time. There's no way to get both a king and a 3 if you only have one card. So for this one, these conditional probability things here, these are giving you like justifications for why they're independent. If you find these conditional probabilities, they all equal 0, right? We saw that is 0, and that doesn't equal 4 over 52. This one's going to be 0 as well. That doesn't equal 4 out of 52. So no on those. And these are typically arguments that things are independent. These are going to be dependents. So are they independent events? No. We know that if one happens, the other cannot. And that's basically the opposite of having independent events. The outcomes are dependent on each other. Yes. So I think it's going to be D. And then probability A and B equals probability A times probability B. So go ahead and try this out. So you do 4 over 52 times 4 over 52. And that should equal the probability of A and B. But if A is getting a king and B is getting a three, the probability of A and B is actually zero. You can't get a king and a three. So when you multiply these two numbers together, you don't get zero. So this one is false as well. So your answer here should be D. These are dependent events. If I get a three, I can't get a king. If I get a king, I can't get a three. That's like pretty core definition of what it means to be dependent. Okay, so last question I'm going to take a look at. This one is talking the two events we're talking about, A and B. A is that your first die is a three, so we're rolling two six-sided dice. So you're going to roll one die and then you're going to roll another. There are 36 possible outcomes. They are shown in this table. So this table shows all the 36 ways you could roll two dice. Let's imagine that the black one is the first dice and the white one is the second dice, or die rather. So what is the probability that the first die is a three? Well, regardless of the six-sided die, there's a 1 out of 6 chance that you get a 3. So I'm going to say 1 out of 6. That's the probability of rolling a 3 on your first die, 1 out of 6. What is the probability that the sum of the dice is 8? So if you know dice probabilities, there's a chance you might know this off the top of your head because you can memorize this, but you can also count them. So out of all of these, how many have a sum of 8? Well, if I roll a 6 first, I need a 2. If I roll a 5 first, I need a 3. If I roll a 4 first, I need a 4. If I roll a 3 first, I need a 5. If I roll a 2 first, I need a 6. If I roll a 1 first, I can't get an 8. So the probability of getting an 8 is 1, 2, 3, 4, 5 out of 36. So it's 5 out of 36. Asking A and B, what's the probability I get both? What's the probability I get the first die is a 3 and the sum is 8? Well, out of 36, how many outcomes are there where that is satisfied? The first die is 3 and the sum is 8. That is literally just this one outcome out of 36. So the probability of getting a 3 on your first die and a sum of 8 is 1 out of 36 to get both of those because you need to get a 5 on your second die. So we'll say this one, 5 out of 36, we said. We said 1 out of 36. And then B given A. So B is the sum of 8s. So what's the probability you get a sum of 8s given that your first die is a 3? You could use the conditional probability formula, but you don't have to because you can just think about, so given that your first die is a 3, there are 6 possibilities where your first die is a 3. One of them has a sum of 8. So there's a 1 out of 6 chance. If you roll a 3 first, there's a 1 out of 6 chance that you get an 8 because you have to get a 5 on your second die. So that should be 1 over 6. 1 over 6 there, but if you're using the conditional probability formula, you should get the same exact thing. So I'll say 1 over 6. That's the probability that I get a sum of 8, given that my first die is a 3. And is that equal to the probability of B? That's what I'm asking. Is B given A the same as B? Basically what that's asking is, does A affect B? Because if you find the probability of B, that's like your baseline. There's a 5 out of 36 chance of rolling an 8. But given that I get a 3 as my first die, I have a 1/6 probability. If I do that out of 36, that comes out to 6 out of 36. So I noticed that the probability went up a little bit. So I have a 5 out of 36 chance of rolling an 8, but if I know that my first die is a 3, I have a 6 out of 36 chance of rolling an 8. And the reason I got 6 out of 36, we agreed on the 1 out of 6, and I just multiplied the top and bottom by 6 so I could compare it directly to 5 over 36, like just for easier comparison. So now I can see their difference. So if I roll a 3 first, I'm a little more likely to get an 8 than if I don't know my first die. So I'm going to say that those two things are dependent because if I know that I rolled a 3 first, I now have a slightly higher chance of rolling an 8. And that should make sense because if you roll a 1 first, for example, you can't get an 8. So if I'm just thinking overall probabilities, I could get a 1 first. That would lower my chance of getting an 8. But if I get a 3 first, I have a 1 in 6 chance of getting an 8 because I just need to roll a 5 on the next die. So I'll say, are they independent? No. So no, they're not independent. And how do I know that? Because B given A does not equal B. That's one way to prove that events are dependent. That's telling me that A has affected the probability of B. All right, very nice. Hope this helps. Have fun.